So the underlying motivation for my work is enabling large-scale scientific computations on modern supercomputers. And I think everyone here knows we're now in the exascale era of scientific computation, meaning we have machines capable of doing 10 to the 18 floating point operations per second. So this clearly offers significant opportunity for scientific simulation and discovery, but with it, it also brings significant challenges in that we actually have to develop algorithms and software that are capable of taking advantage of this powerful underlying hardware. And almost all critical large-scale scientific computations, from medical imaging to combustion to climate science and weather modeling, all involve matrix computations at their core. And a very important point to keep in mind is that these are necessarily inexact matrix computations. And in particular, they're finite precision matrix computations, which is the focus of my work. Okay, so there are many different sources of error, not just finite precision, that come into play in computational science. So we start with some phenomenon that we want to study, and we try and write down some equations that best describe it. And of course, we can't capture this phenomenon fully in most cases, so we necessarily have some modeling error. We then actually need to turn these equations into some discrete problem. So I definitely incur discretization, linearization, or also measurement errors. And then I need to pick an algorithm to solve my resulting problem, okay? And I also make approximations here. So I might approximate my operator in some way, I might use a randomized technique, I might sparsify things, or I might pick a particular stopping criteria for an iterative method. And then, of course, when I actually go to execute this on a real machine, I necessarily incur rounding errors as the computation proceeds. And so these sources of error are intimately connected. So for example, I cannot pick an appropriate stopping criteria for an iterative method unless I have some knowledge about its behavior in finite precision. But unfortunately, in practice, these are often analyzed in isolation of each other. And even further, in many analyses of error, the rounding error is just completely ignored. And this might have made sense in the past, in certain cases, but on today's computers, I hope to convince you that ignoring the rounding error and how this interacts with the other errors is not only potentially dangerous, but is a lost opportunity for optimizing our codes. So in computer hardware as we know it, we only have a finite number of bits to store and compute with numbers. And the industry standard that's been around since before I was here, used by all computers, are the IEEE floating point numbers. And so a base 2 floating point number is shown in this format. So I have a sign bit, I have some number of exponent bits, and I have some number of significand or mantis or fraction bits. And so the number of bits that I assign to the exponent field will determine my range of representable numbers. And the number of bits that I assign to the significand field is going to determine the unit round-off I have. So whenever I store a real number in this floating point format, I incur a relative error that's bounded by this unit round-off. So I'll always use U to represent unit round-off in this talk. And of course, when I have two floating point numbers, I compute some operation on them, and then the result I need to store in this format as well. So I incur a relative error that's bounded by the unit round-off. And so it turns out on modern computer hardware, we have many more precisions to work with than just the usual double precision. So this is a depiction of one node of the booster module of the upcoming Jupiter exascale computer in Germany. And this features 4 Grace Hopper 200 superchips, each of which has an NVIDIA H100 GPU coupled with a 72-core Grace CPU. And a key feature of these GPUs is that they support multiple different precision formats, right? So we now have not only the usual double and single precision, but we also have half precision, quarter precision, we have fixed point formats, we have non-IEEE formats as well. And so the trade-offs are clear, right? So if I have fewer bits to assign to the exponent field, I necessarily have a smaller range of representable numbers. And as I have fewer bits to assign to the significand, I have a larger unit round-off. But the trade-off in performance you can get is significant. So whereas I expect a theoretical peak of 60 teraflops per second if I'm using double precision, if I'm somehow able to make use of these quarter precision formats, I can get up to 4 petaflops per second, and that's on a single GPU. And this is not just theoretical. So whereas this Aurora supercomputer gets just over 1 exaflop on the double precision HPL benchmark, which is solving a dense linear system to double precision accuracy, it gets over 11 exaflops on this HPL MXP benchmark, which is still solving a dense linear system, still to double precision accuracy, but is doing so using mixed precision computation. And so this is, a potential 11x performance improvement. So if we want to maximize the performance of our codes, we need to think about where we can use low precision and how to do this in a way that's safe. And I'll just say that the inclusion of mixed precision hardware in supercomputers is a growing trend, right? So the number of systems in the top 500 ranking of the fastest supercomputers in the world that use mixed precision accelerators is increasing over time. And further, if we look at the ratio of peak compute performance and look at what percentage of that performance is coming from the CPU versus the GPU, we can see that the vast majority of floating point performance is coming from the GPU hardware. So if we want to make effective use of these supercomputers, we have to redesign our algorithms to be hardware aware. That is, to design them such that they can make use of mixed precision hardware available on GPUs and other specialized accelerators. So in designing mixed precision algorithms, we have two goals. So we want to selectively use low precision in the most expensive parts of our code to improve performance, and simultaneously use higher precision in others so that we maintain the desirable numerical properties like stability and convergence and accuracy. And so this is really a non-trivial problem. So first, it requires a rigorous understanding of how the finite precision computation in each part of my algorithm affects the resulting numerical properties. And for many algorithms, for example, for Krylov's subspace method, that means we need to have some understanding about the behavior of nonlinear iterative methods. And of course, this also necessitates developing adaptive approaches. So the right precisions to use in which parts of the code is going to be highly, highly data dependent. So before discussing some of my own contributions in this area, I just want to give you two brief examples to demonstrate the challenges and difficulties involved in using mixed precision. Okay, so my first example of what can go wrong is in constructing a block low rank approximation of a kernel matrix. And so my matrix here is symmetric positive definite, and so it's desirable that my approximation of this matrix retains that property. So I'm just going to take my matrix and generate a 2x2 block low rank approximation. So the diagonal blocks will just be the dense blocks of my original matrix, and the off diagonal blocks I'll represent by rank 1 pieces that I'll compute using a truncated SVD. And so if I compute those off diagonal blocks, those low rank approximations, in exact arithmetic, here's what I get. So I'm zoomed in to the origin here. And so the x's are the eigenvalues of my original matrix, the circles are the eigenvalues of my approximation. Okay, so everything looks fine there, but if I compute this in half precision, now I can see something's happened, right? I've lost positive definiteness. And this would be important if, for example, I wanted to use this approximation as a preconditioner for the conjugate gradient method. So it's important to understand under what constraints on the precision this will happen. So my next example is just running a simple iterative method. So here the conjugate gradient method for solving a linear system AX equals B. And so I'm just taking a very simple diagonal problem here. So my matrix has condition number 1000, equally spaced eigenvalues, right-hand side of all ones. So the simplest problem you could think of. And so here I'm plotting the relative error in the A norm versus the iteration for double precision CG in black, single precision CG in blue, and half precision CG in red. And so it's tempting to look at this and say, okay, this is a great use case for low precision, right? So if I only need 10 to the minus 3 relative error, which is typical for many applications, I can just use half precision, and I'll converge in the same number of iterations as if I had used double. Okay, the only thing that's different here is the attainable accuracy, so where these lines start flattening out. And that's true for this example, but we have to be very careful generalizing this. So here I have a slightly different problem. Okay, so it's same smallest and largest eigenvalues, so same condition numbers, same right-hand side. Now the only thing I've changed is the distribution of eigenvalues. So now the eigenvalues are accumulated towards the left end of the spectrum, meaning I have large outlying eigenvalues, which is a particular case that makes CG more sensitive to round-off error. And so in this case, I can see it's not just the attainable accuracy that's affected, it's also the convergence rate. So if I were to just blindly throw double or half precision at this, I would take more than twice the iterations that I need to converge to the same accuracy as I would in double precision. So that can potentially diminish any gains I got from using low precision in the first place. So we have to be very careful with this. Okay, so I just want to say I'm incredibly honored to be receiving the Wilkinson Prize, especially because my own work in mixed precision algorithms started with work on an algorithm called iterative refinement, which is an algorithm that Wilkinson himself worked extensively on. So iterative refinement is an algorithm that can be used to refine the solution to a linear system AX equals B. And so my basic approach is to compute an LU factorization of my matrix A, use that to compute an initial approximate solution, and then that approximate solution can be refined by iteratively computing the residual, solving for a correction, which can be done reusing the LU factors, and then updating my approximate solution. Okay. And so Wilkinson and his colleagues were using this approach as early as 1948 for solving linear systems on the automatic computing engine. And Wilkinson wrote down a finite precision analysis of this algorithm in block floating point arithmetic, which in 1963, which was then included in his book, Rounding Errors in Algebraic Processes. And so the version of Wilkinson and others at his time was to use one working precision for everything in this algorithm except the residual computation, which is done extra precisely, so in double the working precision. And this was actually, at the time, this was a quite natural use of mixed precision. So hardware at the time could compute an exact scalar product in precision u squared of two numbers in precision u, essentially for no cost at all. Okay, so that was a nice feature of hardware at the time. We'd like to have that back. All right, if anyone has any, okay. And so the theorem that Wilkinson proved, again, it nicely relates the conditioning of the problem to the achievable backward and forward error. So he has a result that says, as long as the condition number of my matrix is safely bounded by 1 over some constant times the unit round off. Okay, so for double precision, that's around 10 to the 16 or something like this. Then the limiting relative forward and backward errors will converge to the level of the working precision. Okay, so again, a nice result connecting the conditioning of the problem to the constraint for convergence. Okay, so I can credit my entry into the field of mixed precision to Nick Hyam, who first suggested this approach to me during one of his visits to NYU, where I was a postdoc at the time. The idea here is that by changing the solver in each iteration of iterative refinement, you can solve more ill-conditioned linear systems. So instead of using the LU factors that I computed at the beginning to directly solve for my correction term, I'll instead use them as preconditioners for a Krylov subspace method, here GMRes. And so we call this GMRes-based iterative refinement. And we've proved that now the condition for convergence instead depends on the condition number of the preconditioned system, which can be much, much smaller, even if L and U are not great in terms of preconditioners. Okay, we expanded on our work in this area, and so the existing approaches for iterative refinement around this time only used 2 precisions. Okay, so there was the Wilkinson type iterative refinement that used a working precision for everything except the residual computation. And also around the early 2000s, it was popular to do what I'll call low precision factorization variants, where a working precision is used for everything except the expensive LU factorization, and this was done for performance reasons. And so it was right around this time, around 2017, 2018, that these half-precision GPUs started to become commercially available. So the idea was, we have at least 3 hardware precisions now. Why not use them all? Okay, and so we have an analysis of this 3-precision iterative refinement where I'm using potentially different precisions for the factorization, the residual computation, and the working precision. And we also have this, I'll call it effective precision, which just allows for the use of a general solver in this step. Okay, and so for example, our results say that as long as my matrix is not numerically singular with respect to the working precision, I can converge to the level of the working precision in backward and forward errors, even if I use a low precision for the expensive factorization part. And this can lead to practical speedups. And in fact, these two ideas in these two papers form the basis, I think, for this new HPL-MXP benchmark I mentioned, which is now established as a complement to the LINPACK benchmark in rating the world's top supercomputers. Okay, so I'm very lucky that since coming to Charles University, I've had a great team. These are my current and former postdocs and PhD students. They all fit on just one slide. Maybe in the future they'll take more, but for now, one slide. All right, and so we've been involved in a number of efforts that having to do with mixed precision. So we were very lucky to be involved with the mixed precision effort under the XSDK branch of the US Exascale Computing Project. And since 2023, we've been leading the ERC Starting Grant project in Exascale, which aims to study the combination of different sources of inexactness, for example, finite precision error and approximation error, in order to develop more efficient algorithms. Right, so the idea here is that if we want to understand what precision we can safely use where in our algorithm, we need new analyses that consider different types of errors together. And this will not only give us some indication of the potential dangers of using low precision, but it will also hopefully present us with new opportunities for balancing errors. So using low precision to improve performance without negatively affecting the other numerical properties that we care about. Okay, so I'd like to briefly highlight a few of my contributions in this area. Okay, so the first involves the computation of sparse approximate inverses, which are a common type of algebraic preconditioner. Okay, let me see if I can get a laser pointer here. Okay, so when constructing a sparse approximate inverse, so I want to construct some matrix M that approximates the inverse of my matrix A. And this is used, for example, this is a type of algebraic preconditioner used in Krylov subspace methods. And so when I'm constructing the sparse approximate inverse, the user has to set this input parameter tau, which controls the quality of the approximation. And so in particular, this tau is the threshold for the required residual norm for the least squares problem associated with each column of my sparse approximate inverse. Okay, and so we've analyzed the sparse approximate inverse algorithm in finite precision, and it turns out that essentially the whole thing can potentially be done in some low precision use of S, but that precision has to be chosen relative to this user input tau. Okay, and so this gives me an indication of how these errors have to be balanced. Right? So what this says is if I only want a rough approximation, meaning my tau is potentially large, then I can safely use a lower precision without degrading the quality of my preconditioner. And we've also shown that you can use this sparse approximate inverse within the GMRes-based iterative refinement framework. And again, we have some constraint on how the working precision has to be chosen relative to this parameter tau. Okay, we've also been looking at mixed precision randomized methods, and in this work we developed a mixed precision variant of a single pass Nystrom method for low rank approximation of a matrix. So here the goal is to compute a rank K approximation of a positive semi-definite matrix, and this is used in many applications. So for example, in approximating kernel matrices in data science, and also in constructing spectral limited memory preconditioners for Krylov subspace methods. And so in this algorithm, the matrix multiplication with my potentially very, very large matrix A is the bottleneck, okay? And so the idea is, can I store and compute with this matrix A in some potentially low precision? All right, and so while people had analyzed the approximation error in these types of methods before, no one had analyzed the finite precision error at all, even in a uniform precision. So we wrote down an analysis of a 2 precision variant of this method. So we have a working precision U and a potentially low precision for the expensive part, this UP. Okay, and we have proved a bound on the finite precision error. So this is the exact Nystrom approximation. The one with the hat is what we compute in finite precision. Okay, and so this is a little hard to parse, but under reasonable assumptions, we can kind of squint at that and we can derive a heuristic that says the finite precision error will likely be less than the approximation error as long as I choose my low precision such that this inequality holds. And so again, this this is the largest eigenvalue here and the kth largest eigenvalue. So this kind of controls, tells me something about the type of the approximation that I want, right? So again, it gives us an indication of how we should balance these two errors. So in general, the greater the approximation error, meaning the closer lambda k is to lambda 1, the lower the precision I can safely use, okay? And I won't notice it because my approximation error is already so high. And we see that this heuristic usually works well in practice. So on the left, I'm plotting for a particular matrix from the sweet sparse collection. So I'm plotting the scaled spectrum in black, and this heuristic for single precision in yellow and for half precision in purple. And so the interpretation here is when this black line crosses one of these horizontal lines, it tells me that if I, so here it crosses the purple line at around 148. And so if I want a rank less than 148 approximation, then I can safely use half precision and I won't notice any effect of that at all in the quality of my approximation. Whereas, regardless of the rank I want here, I could take single precision. And indeed, if we look at the mean total error, it appears that this heuristic works reasonably well. So we do see the purple x's for half precision start to deviate from the others who are all on top of each other at around 148, 150, something like that. Whereas single precision, I do just as well as if I had computed at infinite precision, right? Computing everything exactly. Okay, so the next work I want to highlight has to do with hierarchical matrices. And specifically, we're looking at mixed precision storage for hierarchical off-diagonal low-rank matrices, or Hodler matrices. And so Hodler matrices are kind of the most basic hierarchical matrix you can have. And so here the diagonal, so I have, this is just an example with a 3-level representation, and so, or a 4-level representation. So here the leaf, this has an implicit tree structure, and so here the leaf nodes at the bottom are the dense diagonal blocks. Okay, and in the higher levels, I'm gonna represent these off-diagonal blocks by low-rank pieces. Okay, so the idea here, so usually these are, I'm not going to store these exactly. I'm going to approximate them with, again, some low-rank approximations. And I'm going to call my epsilon here be the maximum relative error in the approximation of the off-diagonal blocks of my Hodler matrix. And so the idea here is if we're already, storing these things, or we're already computing these things in an approximate way, maybe we can get away with just, storing them in low precision also. Okay, so U sub k is going to be the precision that I'm storing the off-diagonal blocks in level k. So I could potentially use different precisions in each of the levels. And so we have a bound here on the total or the global approximation error, which is going to depend on this user input epsilon. Again, you can think of this as coming from a truncated SVD, for example, and the precision that I store, with which I store my off-diagonal blocks. And these C terms here tell me the relative norm of the off-diagonal blocks relative to the norm of the whole matrix. Okay, so again, this is a little hard to parse, but if I kind of turn things around, I can say that this means if I choose the precisions UK to be bounded by this epsilon parameter divided by the relative importance of the block, relative in a global sense, then we essentially don't see the effect of storing the pieces of the matrix in low precision at all. Okay, so that the U's have disappeared from my bound here. And so again, we have an indication of how these errors have to be balanced. And we've also developed an adaptive algorithm that can choose the right precisions automatically during the Hodler matrix construction. Okay, so there's a lot more that I didn't talk about today. So with many collaborators, both external and on my team, I've worked on the mixed precision solution of least squares problems, total least squares problems, preconditioned Krylov subspace methods, using mixed precision within multigrid methods, and also multi-level Monte Carlo methods for uncertainty quantification. And so looking forward, I think it's clear that we're moving more and more towards specialized hardware in our large-scale systems, more towards an era of extreme heterogeneity. And so I think it's more important than ever to take a holistic approach to algorithm design and really consider the whole computational science process, including the hardware that we're going to eventually run our code on. And so there's a huge amount of interesting work, I think, going on in developing new number formats, new arithmetic systems, in developing approximate hardware, approximate instructions, and also the emergence of new computing paradigms like quantum and neuromorphic, and that are hybrids. And so I think the task of analyzing errors from multiple sources and determining how to balance errors in an optimal way to exploit them in these new paradigms will really provide us with a lot of interesting things to do for a long time. All right, so thank you to everyone who supported me in my career. Thank you to the SciAm community for this recognition, and thank you all for being here today.
All right, thank you for a nice talk. Are there any questions for Erin?
Hi, thanks for the very nice talk. In terms of some of these metrics, for example, when you gave like the conjugate gradient and the number of iterations that it took to solve, and I think that was like not your work, but just a sort of general question. I guess this also depends on the metric, because if you can do, say, like 4 times or more than 4 times as many floating FP16 operations as you can do FP64, then overall it might still be better to run the FP16. Is there work being done on sort of considering this, or using, heaven forbid, we've done this in the past, but you time at startup which algorithm you use, which makes it annoying because your code is never reproducible, but you know, it runs faster.
I mean, I think yes, I mean, it's highly, something that's highly problem dependent, and so I think it's difficult to do anything a priori at all in a general sense. I mean, usually when we think about running Krylov subspace methods, we think about running them on very sparse matrices, which you know, aren't going to see typically the 4x improvement that you get doing dense computations. And so it is potential. You have to look at the specific structure of your matrix and kind of determine from that, what potential speed up I expect to get from doing things in low precisions, and somehow also balance that with the finite precision. So it's a difficult problem to do, I think.
Okay, thank you. It looks like, I don't know if there's anyone else right now. I have another question on sort of, for the multi-grid, is it basically you can switch to lower precision on the coarser resolutions? Is that the idea?
So there has been, so McCormick and others have done work on that and analyzing that. So here we're just, we're looking at using low precision in the other parts of the smoothing operations.
Okay, thank you.
Yeah.
We're out of time. All right, I want to thank Erin one more time, and congratulations.
Thank you.